This lesson is going to be on something called the second fundamental theorem of calculus, which is really kind of an extension of the fundamental theorem of calculus that you learned in the last lesson. It's going to deal with the definite integral again, but this time it deals with the definite integral as a function. Instead of the definite integral as a value of an area under a curve, this time the definite integral will be a function. So it's kind of the same stuff, or building off of the fundamental theorem, except now instead of two limits of integration, two numerical limits of integration, you're going to have a variable limit of integration. So therefore the definite integral will be a function, and that's what we're going to look at here. So for instance, we have f of x, capital F of x, is equal to the definite integral from 0 to x of cosine of t dt. So now this is what we call an accumulation function. F of x, this function here, is going to be the area under this curve, under the cosine curve, between 0 and some number. So as this value of x increases, the value of the definite integral changes. Therefore, the definite integral is a function. So f of x is a function, is the area under the curve as that x value changes. So therefore, the definite integral is not a constant number, it is changing. So, let's plug in a few numbers. Evaluate this for x is 0, pi over 6, pi over 4, pi over 3, and pi over 2. Find a few values. So if you plug in 0 for x, remember 0 is x, then evaluate the definite integral from 0 to 0 of cosine of t dt, meaning the area under the cosine curve between 0 and 0. So there is no area under the cosine curve, so f of 0 would be 0. Now if you plugged in pi over 6, you would get the definite integral from 0 to pi over 6 of cosine of t dt, meaning the area under the curve of cosine between 0 and pi over 6. So this area here, so you would be gaining an area. If you went to pi over 4, you'd be going from 0 to pi over 4, so it would be bigger. Pi over 3 would be even bigger. All this area, pi over 2, you get this whole piece right here. And if you continue beyond that, the cosine curve goes under, so your value will be getting lower. So the the value of the integral, f of x, is the value of the integral between 0 and some x value of the cosine of t dt. Notice these two numbers can't be the same. Well, in order to evaluate a definite integral, we can use the fundamental theorem of calculus. So we're going to antiderive cosine of t, which will give us sine of t. So in order to find f of x, we're going to find sine of t between 0 and x. So we plug in f of b minus f of a. Sine of x minus sine of 0. Sine of x goes in for t, minus sine of 0 goes in for t. And the sine of 0 is 0, so capital F of x equals sine of x. The area under the curve between 0 and x, under the cosine curve, will be the sine of whatever that x value is. And you see you have the table here to get those exact values. And you can see that these numbers are increasing. 0, if you're going between 0 and pi over 6, you're up to a half. 0 and pi over 4, you're up to square root of 2 over 2. Pi over 3, you're up to square root of 3 over 2. 0 and pi over 2, you're up to an area of 1. So the area is increasing as this x value goes to the right. As I said, if we continue, this would start going down, so your area would go back down again. Now we're going to look at a couple more examples. Capital F of x equals the integral from 0 to x, again, a function of this top number of t plus 2 dt. So the area under the curve of t plus 2, a line with a slope of 1, between 0 and some x value. So as you move to the right, that area is going to be increasing. So you antiderive 1 half t squared plus 2t from x to 0. So you plug in x, 1 half x squared plus 2x, minus plug in 0, you get 0. So capital F of x equals 1 half x squared plus 2x. Find the area under the curve of t plus 2 between 0 and x. Do 1 half times x squared plus 2x. Now we have capital F of x equals the integral from pi over 4 to x, from some other constant to x. We're still starting with a constant, it's just not 0 as our constant. Secant squared of t dt. Antiderive secant squared, you get tan of t from pi over 4 to x. Plug in x, you get tan of x. Plug in pi over 4, you get tan of pi over 4. Take the difference using the fundamental theorem. So you get tan of x minus 1, because tan of pi over 4 is 1. So capital F of x here equals tan of x minus 1. All right. Now the second fundamental theorem deals with the definite integral as a function, but it more so deals with the derivative of that function. So we're going to look at three derivatives that we just did. F of x, capital F of x, was the integral from 0 to x of cosine of t dt. We found that equaled sine of x. Well, if I take f prime of x, if I derive sine of x, f prime of x equals cosine of x. F of x here was 1/2 x squared plus 2x. That was the integral from 0 to x of t plus 2 with respect to t. Well, f prime of x is going to be 2 times 1/2 is 1, x to the first plus 2, x plus 2. And now we have a function we started somewhere other than 0. This bottom number was a constant other than 0. Capital F of x was tan of x minus 1. The derivative of tan of x is secant squared of x minus 0. So f prime of x equals secant squared of x. You look at all three of these and the results. Capital F of x is the integral as a function. Capital F of x is the integral as a function. Capital F of x is the integral as a function. All these integrals are with respect to t. All of the functions are functions of x. Well, when you derive f of x, when you derive the integral with respect to t in terms of x, you can kind of see you went from f of x is the integral of cosine of t. Well, the derivative was cosine of x. It's t plus 2 dt. Well, the derivative was x plus 2. Secant squared of t, the derivative is secant squared of x. So as we anti-derive, plug in the x value, then derive again, what basically happens is the variable inside is replaced by an x, the variable outside. T plus 2, x plus 2. Secant squared of t, secant squared of x. And this leads us to the formal second fundamental theorem of calculus. The derivative with respect to x of a definite integral from some constant a, could be 0, could be pi over 4, could be any other constant, from some constant a to x of the integral of f of t dt, some function of t with respect to t, is just going to turn into a function of x. This constant term at the end gets wiped out when we antiderive and then derive again. So, what we're doing is basically replacing the value of t with x. The function in terms of t now becomes a function in terms of x. When we antiderive this, plug in our x term, then derive again, the x's remain. Now what you want to do is you want to be careful. If the upper limit is a function of x, it's not just x, it's x squared or 5x to the 5th or tan of x or any other function of x, it's not just x. You want to apply the chain rule when you use the second fundamental theorem. So if capital F of x equals the integral from pi over 2 to x cubed, from some constant to some expression in x, some function of x. Well, you're still going to do the same thing. You're going to insert this everywhere you see t. So it's going to be the cosine of t. Instead of cosine of t, I should say it's going to be the cosine of x cubed. But when I antiderive this, I would get sine of x cubed. And then when I derive it, I would get cosine of x cubed times the derivative of what's inside, which would be x cubed, so you would get 3x squared. So when your upper limit is a function of x, other than just x, you're going to insert it everywhere you see your t, or whatever variable you're anti-deriving or integrating with respect to, and then at the end multiply by the derivative of that upper limit. So the 3x squared gets multiplied by the cosine of x cubed. Alright. That was the second fundamental theorem of calculus. Now what we're going to do in these next couple slides is different. It's not the second fundamental theorem. So kind of get your mind set on this is something a little bit different than what we just did. Now we're not deriving integrals that are functions themselves. Now we're going to look at a couple applications of definite integrals. So you have this problem here. A chemical flows into a storage tank at a rate of 180 plus 3t liters per minute, where t is between 0 and 60. So that's over an hour. Find the amount of chemical that flows into the tank during the first 20 minutes. So we are given a rate. You're given a rate. And you want to find out, okay, this is the rate something is flowing into a tank in this case. You want to find out how much actual chemical is in the tank over a period of time. So if I graph that rate, 180 plus 3t, so you're going to get a linear function. And I look at my units on each axis. The horizontal axis would be my time in minutes. The vertical axis would be my rate, whatever this rate is, liters per minute. Well, if I want to find total liters that flowed into that tank, I could take liters per minute, multiply it by minutes. The minutes would cancel, I'd be left with liters. So if I multiply the vertical axis by the horizontal axis, I'm finding the area under the curve. So this is one application of the definite integral. I'm going to use the definite integral to find the total amount of change, the total amount that accumulated, the total amount of displacement, the difference from where it started of a rate. So I have the integral, in this case they went over the first 20 minutes, so I'm going from 0 minutes, so that's just when it started, to 20 minutes of this rate, of the rate it's flowing in there. So I integrate the rate function. So 0 to 20, 180 plus 3t with respect to t. And I derive 180t plus 3 halves t squared from 0 to 20. You could even type this in your calculator. If you did it by hand, you would get 4,200 liters. So if you know this is the rate, the chemical? The chemical is flowing into the tank, and you want to know how much total chemical has entered the tank over a period of time. You can integrate the rate function with a definite integral, and you would get the total amount of liters. Liters per minute times minutes gives you liters. Okay, next, a two-part question involving a particle in a horizontal motion, a particle moving along a line. The particle's moving along a line, so that its velocity is v of t equals t cubed minus 10t squared plus 29t minus 20 feet per second at time t. Again, they gave you an equation for a rate. Velocity is a rate. So, first thing we did with this, we're not going to want to graph this by hand. Get it in your calculator. y1 equals x cubed minus 10x squared plus 29x. You can see the minus 20 expanded enough. Obviously, you've got to change your t's to x's in order to use your calculator to get this. Then, you want to look at the picture. Well, here's the velocity function. This is the rate function. This wants to know what is the displacement of the particle on the time interval 1 to 5. So from 1 second to 5 seconds, where's the displacement? If the particle started here, how far away from here is it? Did it move right? Did it move left? If it's positive 7, it would be 7 units to the right. Negative 2 would be 2 units to the left. You want to know how far it is from where it started, the displacement, the net change from where it started to where it is at the end of the interval. Well, again, this is a rate. So if you integrate the rate, you got feet per second on your vertical axis. You have seconds on your horizontal axis. Feet per second times seconds. You would get total feet displaced. So you integrate from 1 to 5, v of t, this function with respect to t. Little shortcut that will help you, especially as we get down the road to some more complicated functions that you can't integrate by hand. You could solve this by hand using the fundamental theorem. You have the tools to do this. But to speed up the idea a little bit, speed up the process, we're going to let the calculator do some work here. The setup's what's important here. If you understand that this question is asking you for this definite integral, then going through this by hand with pencil and paper isn't as important. Getting to here is what's really important. Now, applying the definite integral to a problem, to a particle motion problem in this case. In the calculator, I already had y1 equal to this equation. So I'm going to integrate from 1 to 5. y1, and I have to put with respect to x because I plugged in these t's as x's. So you can use the calculator to get this answer. You don't have to type it all in. Once you graph it, you can use the y1 button, and it'll use the first equation in your list. So the integral from 1 to 5 of y1 dx gets you 10.6 continuing. If you want to turn it to a fraction, 32/3. So that means that this particle is 10.6 units to the right of where it started. From at 1 second it's here, 4 seconds later at 5 seconds it's 10.6 seconds to the right. It's that far displaced. That's its net change over those 4 seconds, from 1 second to 5 seconds. Now, next type of question they could ask you. This particle, you can see, is moving in a positive direction over here because the velocity is positive, but over here it's moving to the negative direction. It looks like at 4 seconds it started moving backwards. So it was moving to the right, at 4 seconds it stopped and started moving back to the left. And at 5 seconds it was here, 10.6 feet away from where it started. But the next question is going to ask you, what is the total distance traveled by the particle over that time interval? So it moved from here, way down here, and came back. So the displacement's a difference between them. But you also have this point from here to here, and back again. It traveled. So the total distance it traveled takes into account the area under this curve and the positive area under this piece of the curve. Because even though it's traveling in a negative direction, it's still moving a distance. So, in this case, you want to integrate the absolute value of the velocity. We're going to count this as a positive distance, this area under the curve, because it wants the total distance, not how far it is from where it started. And again, use your calculator to solve this. Integrate from 1 to 5, absolute value of y1 with respect to x. And you can see it's a little bit more, 11.8. So it was moving, and this little end part, it went back and forth and stopped at 5 seconds. Not really stopped at, but where it was at 5 seconds, accounts for a little over 1 more foot of distance traveled. So, the function traveler ended up 10.6 feet away from where it started, but it traveled 11.8 feet because it went over and it was coming back when we stopped and took that measure. So remember, displacement or the net change, the difference from where it started, is going to be the integral of your rate. The total distance traveled accounts for a positive direction and a negative direction. That's going to be the integral, the definite integral of the absolute value of your rate.